Hello everyone, my name is Alton. In this video, I'm going to show you how to find maxima and minima using Lagrange multipliers to solve optimizational problems with one constraint for functions of two variables. Throughout your calculus journey, you're going to find such problems are embedded in real-world applications, and we use these methods in effort to maximize and minimize dimensions, cost, and areas. I want to also take the time to recognize Mr. Frankie Nolan, a former student of this class, and he made a video about right triangle trigonometry. It has nothing to do with this, but it's an amazing video, and you're gonna leave this class knowing a wealth of right angle trigonometry, right triangle trigonometry rather. It's a good video, not too long, and he's the way he explains it is very great. He's also doing one other video, I believe, and I'm gonna upload them both to this website. Without further ado, we're gonna think of this overview as things you need to master. Okay, we want to master the use of Lagrange multipliers to solve optimizational problems with one constraints for functions of two variables, and it's important that we know or keep in mind that there exists a constraint function, g of x, y, which equals to 0. And we need to ensure that this equation equates to 0. And this concept may confuse some of you, but I find it best to just dive right into the learning experience to better understand how to figure out these these problems of optimization. All right, so here we have our first problem. It's a real world problem that aims to produce the maximum total area of fencing. And in these problems, we need to be able to visualize and interpret a demonstrative of what we're trying to solve. I'm gonna read it first. 3 pins of the same sides are built along an existing fence. If 320 feet of fencing is available, what length should X and Y be to produce the maximum total area? What is the maximum area? All right, so we have 3 pins along an existing fence here. 1 pin, 2 pin, 3 pin. All right, the existing fence is the highlighted portion. Okay, we also notice that this is some sort of rectangle. Okay. We're then gonna next label our demonstrative, so to speak. And typically when we're labeling these sort of questions, it doesn't matter what letters we use. Usually Y is used as a vertical axis and X is usually used as a horizontal axis. But it really doesn't matter. I'm going to show you guys how to do it the opposite way, where we're going to have X being our vertical axis for these bounds, and Y is going to be our horizontal axis, okay? Now, I don't want you guys to fester on this concept that I'm going to bring up, but I need to show you guys the method of Lagrange multipliers for the function of two variables, okay? It's depicted in this picture here. This picture shows that we can find the maximum and minimum of the two variable function f x y subject to the constraint g x y equals 0, okay? And this is how we're going to tackle Lagrange multipliers, all right, which is our first step. All right, so as you guys notice, the first step would be to find fxy, notice the lowercase, equation, which is the function to maximize or minimize, and we want to find our gxy equation, which is the constraint. All right, so we're going to find the function to maximize or minimize and our constraint function. And since we want to maximize f equals xy, we're going to find out what that is, in fact. And it so happens to be the area of the rectangle. Usually it's known as the area of the rectangle's length times width. We have an x and y value, so it's just going to be fxy equals xy. We have our width and our length, okay? And it's okay to have letters as values here. And now we're going to find gxy, all right? And it's derived from the parameter. So I want you guys to visualize something really fast. we have 3 pins, okay, along an existing fence with only 320 feet of fencing available. So what we're gonna do is get all of our x, y values into this equation and add them up to each other, okay? So here we have 4 x's present. 1, 2, 3, 4. So we're gonna write 4x. I want you guys to keep in mind that we only have one y, okay? We don't have 2 y's. This y is already existing, and there's no need to build a fence that exists already, okay? And we're gonna make sure we also, since this is the parameter function, include that there's 320 feet of fencing available. And if we want to be lazy about it, we're gonna probably think that this equation is gonna equal to 320. But that's where you're wrong, okay? We shouldn't do that. We are gonna instead make sure that our gxy equals to 0, okay? Just like I stated in the disclaimer. It's so important that we do that. We're gonna actually have fx plus y minus 320 equals 0. gxy equals 0, okay? And I know some people are kind of rusty. I don't know how long you've been viewing algebra equations, but in order to do that, to put our 320 feet to 0, our g of x, y function to 0, we're gonna just simply subtract all values that are on the right side to the left side. And that's how you're gonna do that algebraically. All right, so our second step, it's a process called finding a capital F x, y, lambda. And this is called creating an equation with Lagrange multiplier formula. Okay, so Lagrange multiplier formula is here. I don't know if you can see it in the step 2, where capital F x, y, lambda equals fxy plus lambda gxy. Okay, and we're going to go ahead and do that here. So we're going to make our equation. I'm going to write that again for you guys so we don't have it fresh in your mind. fxy lambda equals lowercase f xy plus lambda g xy. This is the equation with the Lagrange multiplier formula. This is the equation that we're trying to obtain, okay? So this part is really simple. We're just gonna plug in what we have in step 1. And we're gonna see that it equals fxy is xy, okay? Plus gxy, lambda gxy rather, which is gonna be this gxy. Minus 320. Okay. Our next step would be to distribute the lambda to the parentheses. And I'm not writing that again. That's going to be xy plus 4 lambda x plus lambda y minus 320 lambda. All right, and don't let all these letters confuse you, okay? Just have faith that you can solve this problem, and you're gonna get a gist of what we're doing closer to the end, okay? So just bear with me. We're gonna move on to our third step. All right, this step is going to involve some of your calculus education. I'm not sure how comfortable you guys are with partial with partial derivatives, okay? But if you're not comfortable, you're gonna have to go back to partial derivatives or find a learning resource that's gonna help you understand this concept, okay? And work our way through the problem because I assure you it's not really difficult, okay? But it does take some attention. We're going to use this to find capital F x, capital F y, and capital F lambda, which is our partials, okay? And then we're going to set these partials to 0. So we'll begin with the capital F x, which equals to y plus 4 lambda, okay? Because the derivative of xy is y, and the derivative of 4 lambda x is x. Lambda y would be 0 because it's not used in respects to the letter in our Lagrange multiplier, right? And negative 320 lambda is 0 as well because there's no letter in our Lagrange multiplier that correlates to the two. Okay. And we're going to equate this to 0. It's that simple. Now we're going to move on to our f of y, capital F of y rather. And we see here that the derivative of 4 lambda x, we'll start off with the y, xy. The derivative of xy in this instance will be x plus the derivative of lambda y, which is just lambda, the derivative of 4 lambda x does not correlate to these y values, and same goes for this last, negative 320 lambda, okay? We're going to set that equal to 0. All right, finally, we're going to find capital F lambda, which will equal the derivative of xy with respects to the the letter in our Lagrange multiplier, right? This is going to be 0 because there's no lambda in it. This is going to be 4x, okay? The derivative of 4 lambda x is just 4x, plus the derivative of lambda y, which is just y, minus 320. Which is the derivative of negative 320 lambda. But we're not going to include the lambda, like I almost tried to do. We're going to set that equal to 0. All right, now we're going to take fy and solve for x in step 4. This step is going to be algebra intensive, so to speak. So we're going to take everything that we've learned in algebra thus far, whether it be substitution, elimination, or anything else you might come up with, PEMDAS. And we're going to be flexible in order to solve this problem. Okay? The first step, we're going to solve for fy. We're going to take our fy and solve for x. That's going to be fy equals x plus lambda, which equals to 0, right? And now we're going to solve for lambda. So lambda is going to equal to negative x. And now we just subtract the negative, in this case, we just subtracted the x to the other side. And we have a negative x, and we don't want that. We want to have x all by itself. So we're just going to divide negative x by 1. And that's going to let us have a negative lambda equals x. So great, we got x all by itself. Next, we're going to take capital F x. We're going to equate that to y plus 4 lambda. We're going to make this equal to 0. All right. So now 4 lambda equals negative y. All right. We're going to divide by the negative 1, just like we did in the problem above, so that we can get y by itself. So we're going to have negative 4 lambda equals y. Good. Next, we're going to use our f lambda equation and plug in the values for x and y. And that's going to get us f lambda, which equals to 4x plus y minus 320 equals to 0. Okay. We're going to plug in our values. F lambda equals 4 negative lambda for x plus negative 4 lambda minus 320. And that's going to equal to 0. So we do some solving with algebra, like I said, and that's going to give us negative 4 lambda minus 4 lambda equals to 320, which equals to negative 8 lambda, which equals to 320. All right, we're going to divide each side by 8, or negative 8 rather, and that's going to get us a value of negative 40. Okay, so we found our lambda. Lambda equals negative 40. Now that we have lambda, we can use this to find x. And what did we say x was? X equals negative lambda. Negative lambda, negative 40 equals x. And we'll see that x equals 40, which equals to 40 feet. What do you know? We found our x value. That's a big feat. So you guys should be proud of yourself. All right, the next step would be to find our y value. We deemed it to be up here. Let me move this sidebar out the way. I don't want to confuse anybody. We're going to take our y, bring it on down here, and we're going to plug in our lambda. So negative 4, negative 40 equals y. All right, we're going to do some multiplication and find out that y equals to 160, which equals to 160 feet. What do you know? All right, the problem asks us to find the maximum area, okay? And in order to find the area, we all know that x times y equals the area of a rectangle square feet. So when we multiply our x and y, we're going to go ahead and get 6,400 feet squared. And that is the maximum area. All right, that is the length x and y should be to produce the maximum area, which is 6,400 feet square. All right, I'm going to let you take this in. And then we're going to move on to our next question. All right, so throughout your calculus educational path, you're going to also use Lagrange multipliers of two variable functions to solve bare functions and constraints. All right. Here we have a bare function, f(xy), subject to the constraint negative 6x minus 4y, which equals to 52. Okay. And these are the sort of problems you might find in your very own calculus class. Okay. That's kind of away from real world application, you know. But everything's going to be the same pretty much. These 4 steps are going to apply to this as well. We're going to use the method of Lagrange multipliers. And they're asking to minimize this function here, f(xy). Okay, and we can do that. All right, because we're using this method of Lagrange multipliers to locate any local maximum or minimum of a function. Okay. All right, so we're gonna dive right in. Our first step is to find f(xy) and g(xy). f(xy) is clearly listed here. Okay. There's no denying that fxy equals to x squared plus y squared. All right? It was simply given to us. Gxy, we know must equal to 0. And we have 52 here, so in efforts to do that, we're going to subtract it from the right side to the left side. All right? Very simple. Don't miss this step because we're going to have a hard time down the line rectifying that. Minus 52 equals to 0. And step 1's done. You should be proud of yourself. All right? Now for step 2, we're going to find our equation with Lagrange multipliers, okay? Which we know is capital F rather, pardon me, xy lambda equals to fxy plus lambda gxy. Great. When we rewrite this, we'll find out that we have fxy lambda equating to x squared plus y squared, and in this case minus 6 lambda x, because don't forget to multiply lambda to this parentheses here. So we're going to have negative 6 lambda x minus 4 lambda y minus 52 lambda equals to 0. And that's it for step 2, okay? Step 3, we're going to find capital Fx, Fy, F lambda. It is important to know how to use derivatives again in integrals, in calculus, period, okay? And some of your knowledge of partial derivatives is going to carry you through all these type of problems. So you're going to need to really refresh up on your partial derivatives. All right, and we're going to find our partials with respect to the corresponding letter in our Lagrange multipliers, like we said before. Here's a quick picture. All right, first off, we're going to start with capital Fx. We're going to make that equate to 2x, which is the derivative of this. This is going to go to 0, minus 6 lambda. All right, we're going to set this equal to 0 because everything else goes to 0. We have no x values here. All right. Now we're going to find Fy, which equals to 2y minus 4 lambda. We have the derivative of y squared and the derivative of negative lambda 4. All right here. Then we're going to equate this to 0. Are we done? No, we have one more, capital F lambda, which is going to equal to negative 6x, the derivative of this here, minus 4y, the derivative of this, minus 52 equals 0. All right, I'm going to go ahead and lower this off so we can have space for our step 4, which we all know is the part we know and love, which is the algebra. Please be flexible in doing all sorts of algebraic techniques in order to solve these problems, because if you made it this far in your academic career, you definitely know how to do this. So just have faith. So we're going to solve for x, y, and lambda using algebra. So first, we're going to take this fx, capital Fx equation to get x alone. So we see that 2x minus 6 lambda is going to go ahead and equate to 2x 6 lambda, with x equating to 3 lambda. All right, that's what x equals to for now. And we're going to do the same thing for capital F y. All right, bear with me one second. All right. Fy is going to equal to 2y minus 4 lambda, which in turn is going to go to 2y equals to 4 lambda, which then equates to y equal 2 lambda. And this is simple algebra that I know you guys could do. All right. We're going to plug these into our lambda equation from step 3, okay? So our lambda equation was capital F lambda, which equated to negative 6x minus 4y minus 52. And that all equated to 0. Next, negative 6. We have our x value, which is 3 lambda. We're going to plug that into wherever we have an x. That's called direct substitution, okay? Minus 4, 2 lambda, which is our y value, okay? Minus 52 equals to 0. All right, we're going to do some multiplication. And we're going to find that negative 18 lambda minus negative 8 lambda equals to just 52. All right, now we're going to move that negative 52 to the right side. All right, all that's going to equal to negative 26 lambda equals to 52. So we want lambda by itself, so we're going to divide negative 26 from lambda. And when we do that, we're going to find out that we have a value of negative 2. Don't forget there's a negative value here. So we have our lambda. All right, now we can plug lambda into our x and y equations, okay? So we'll start with the x, which equals to 3 lambda. When you plug in negative 2, you're going to have a value of x equating to negative 6. And that's it. We got our x. Now we're going to have our y up here, which equals to 2 lambda, which equals to negative 2. Now we have a value of negative 4. All right. And we just answered the question. The x coordinate of the minimum was, what did we say it was? Negative 6. Good job. The y coordinate, negative 4. We plug that in here. All right, the value of f at the maximum is, could you guys guess? All right. The value of the maximum is going to be whatever we plug x and y into the function that we want to maximize and minimize. So don't forget that the function we want to maximize and minimize is our f of x here. All right, f of xy rather, excuse me. So all we need to do, in this term, we do want to minimize too. So we're not maximizing here, we're minimizing, but same process. F xy equates to negative 6 squared plus negative 4 squared. And all this is going to equate to 52. All right, we're gonna see how true that is. We'll plug that into a calculator, and we're gonna find that the minimum is in fact 52. So you guys just did that problem correctly. All right. You made it this far. You should be very proud of yourself. We're going to go through one more problem. And this one I'd say is a little tricky. I'm going to read it first and then kind of talk through it with you. So the The Cobb-Douglas production function for a particular product is nxy, which equals to 60x to the power of 0.6, y to the power of 0.4, where x is the number of units of labor and y is the number of units of capital required to produce nxy units of the product. Each unit of labor costs $60, and each unit of capital costs $120. If $600,000 is budgeted for product production, determine how much how much amount should be allocated to maximize production and find out the maximum production product. Allocate to maximize production and find the maximum production. Okay. All right, the product will be maximized when using blank units of labor and blank units of capital, and the maximum production is blank. That's what we want to find out. All right. All right, so for this step, same thing. Don't let the words confuse you. It's actually pretty straightforward here. We find that we do have a function of which we want to maximize in this case, okay? And what do we know about the functions of which we want to maximize? They are f of x, y, okay? So let's not forget that. In this case, nxy is going to be the fxy, okay? So we'll just replace this f with the n, okay? Just like here. That's the function that we want to maximize. We're going to equate that to 60 x to the power of 0.6, all right? And that's going to also be multiplied to y to the power of 0.4, okay? All righty. So we have our fxy, so to speak, but in the form of nxy. You know what? In order to, I'm not going to confuse you. We'll keep it nxy, but just remember that this is fxy. All right, the next step is to find our constraint. All right, and what is that? Okay, we know that we have unit. Excuse me. You know that we have a unit labor cost, right? And we have units of capital. All right, so which one is which? X is going to be the number of units of labor, and Y is going to be the number of units of capital. So we have the labor, which is X. It equates to $60. And we have capital costs, which is $120, and that equates to the value of Y. All right, so let's take that in. We want to formulate a g of x, a constraint, so to speak, that is budgeted for $600,000. All right, that's our constraint. So that's kind of the parameters of which we're working in, okay? So we use this information here in the word problems to formulate our g of x. All right, so just bear with me. Don't get too flustered about this problem. It's really simple. We found our f of x. Now we're going to do our g of f of xy. Now we're going to do our g of xy. So 60 is our x in this equation, okay? Which is the labor of the cost of labor. And we're going to add this to ry. Ry is the units of capital, $120. All this is going to be budgeted from the $600,000 equation. So we don't want this to equal $600,000. We want to subtract that so we can make the g of x equal to 0, just like the last problem. All right, perfect. So the second step is to create the equation for Lagrange multipliers. All right, we all know that equation now. I don't want to beat a dead horse, but we're going to have fx equals 60. And we're going to also take the derivative in this process, okay? And we're not going to forget our power rule, so to speak, okay? So we're going to have 60x, which is going to be 0.60 x to the power of negative 0.4, right? And we're going to have y Oh, you know what? I'm moving too fast for you guys. Let me go ahead and write out this equation. Okay. F x y lambda is going to equate to 60x to the power of 0.6, y to the power of 0.4, plus 60 lambda x plus 120 lambda y minus 600,000 lambda. All right, that's going to be our equation of Lagrange multipliers. All right, the third step is going to be the step I almost completely jumped over, being too eager. Now we're going to find our partials with respect to the letters in our Lagrange multipliers. Same step. Okay, there's nothing new. Don't get ahead of yourself like I almost did. So we have our fx, capital Fx, all right? We're going to keep the 60 here, right? But using the power rule, which is the exponent minus 1 over the exponent minus 1. Let me erase that. That's why it's important to know your derivatives. We're going to have the value of 0.6x to the power of negative 0.4. Okay. 1 minus 0.6 is negative 0.4, which is our derivative, which you should know at this step. It's very important. All right. Y is going to be, what's going on with Y? Well, Y is attached to this. This whole problem's Y. XY is this function here. So we're only gonna focus on the X portion of this one, okay? So Y is gonna remain the same in this instant. Alrighty. Now we're gonna add some more functions. We have the derivative of 60 lambda x, which is in turn gonna just be 60 lambda, right? And in this instance, since we have no more x values, everything else is going to go to 0. There's no x values here. All this is going to 0. So we don't include this. And then we're going to equate the equation to 0. All right. Next, we're going to have capital Fy, which equals to 60x to the power of 0.6. Nothing changes here. But y is going to be subject to the power rule. Like so, okay? And when we do that, all we're gonna do is, bear with me. We're gonna subtract, oh wow. We're gonna do the derivative. So we're gonna bring that top value down. It's gonna be 0.4 y, 0.4 minus 1. It's negative 0.6 now. Okay. And that's gonna be multiplied to that. And now we're gonna find our other derivatives here. So in this case, we have no y's here, so that's gonna be 0. But the 120 lambda is going to be 120, or the 120 lambda y is just going to be 120. Okay. All right, so now we have our capital Fy. We're going to equate that to 0 and move on. Capital F lambda is going to equal 60x because there's no lambda anywhere else in this equation. These are all xy values. So that goes to 0. the derivative of 60 lambda x is just going to be 60x. And we're going to add 120 lambda y, which is going to end up being 120y because the derivative of 120 lambda y is just 120y. And we're going to also include this negative 600,000 lambda, which is just going to be 600,000. And equate that to 0 as well. All right, so we're going to notice something very peculiar about this whole thing. This is going to be our g of x, y, which we see here. And when we do our algebra, we're not going to have to rewrite this really if we don't want to, okay? It's just since it's the same as the g of x, y in the step 1, okay? We don't need to rewrite this anymore. So let me erase all this. All right, I'm going to minimize this, and then we're going to start solving some algebra. Oh, technical difficulties here. Give me 1 second. All right, I'm just going to make a big section down here. Solve for x, y, and lambda using algebra. All right, so the first thing we're going to do here is going to write down our function for fx, which is going to equal to 36 to the power of negative 0.4. Y to the power of 0.4 plus 60 lambda equals 0. And the reason why we have 36 here is because when we multiplied 60 times 0.6, when we used our power function to find our partial derivative here, that's the value that the calculator is going to give you. All right, just so you're not confused. And I'll keep this up so you guys can kind of see what I'm going by. All right. Now we want to start moving everything to the right in efforts to get lambda by itself, like we've done in the other equation. So forgot to include lambda. And yeah, when we do that, we're going to see that we have 60 by itself. And that's going to equate to negative 36 x to the power of negative 0.4, y to the power of 0.4. Okay, then we're going to divide by 60 to get lambda by itself. So let me duplicate that, bring the 60 down, and we have our lambda here. Okay, we're going to do the same thing for y as well. Let me bring everything in a compact way so it can be nice and neat for you guys to visualize. All right, we're going to do the same thing for fy. Okay, so when we multiplied 0.4 times 60, we have a value of 12. So fy, or a value of 24. When we multiply these two, we have the value of 24. All right, so we're going to have 24 x to the power of 0.6 y to the power of negative 0.6, because we use the power rule of exponents. Don't forget derivatives. And that's going to be added to 120 lambda. All right, we're going to equate that to 0. So same thing, move everything to the right hand side in efforts to get lambda by itself. All right, It's going to equal to negative 24x, 0.6y, negative 0.6. And same thing. I'm going to divide this by 120 in order to get lambda by itself. Woof! A lot of work. So if you guys notice, we have a situation where both lambdas are equal to the same equation. And I want you guys to kind of think about what that means. That means that we have two equations that equal each other. So we could simply do something spectacular here. Equate these equations to one another and cross multiply. And this is going to save us a lot of hardship. And when we do that, we're going to have a value of negative 4,320x to the power of negative 0.4 and y to the power of 0.4. Okay? And that's going to equal to, when we multiply 60 times negative 24, we're going to get a value of negative 1,440 x to the power of 0.6, y to the power of negative 0.6. All right. Now, our next step in this whole ordeal, let me make this a little smaller as well. The next step in this whole ordeal is we want to move these y terms to each opposite side. All right. And kind of correlate. We want the negative values to go in their denominators. And when we do that, we're going to have a value of 4,320x, or my apologies, y 0.4, because we want the y values with the negative values at the denominator. Okay, so we're going to move y to the left. We're going to move x to the right. And when we do that, we're going to have these two equations here. Y negative 0.6 and negative 1,440 x 0.6 with the value of x to the negative 0.4 here. All right. So when we want to divide these, how should I say, y's with the same base and different exponents, we're going to subtract them, which gives us the power of 1. Okay, so when you subtract this with this, because that's how we divide exponents, we're actually going to add them together, because when you're going from the denominator to the numerator, you're going to add if you have a negative value. Okay, and what's 0.4 plus 0.6? It's just going to equal to 1. All right, so that means that negative 4,320 y is just going to equal to 1. So that's just negative 4,320 y. And same thing on the other side. We're going to add this to the numerator, and that gives us negative 1,440 x. I'll bring this down here. Now, we're going to solve for x in this instance because I kind of want to have a bigger value, and I know if I divided this large number, even though it's essentially a negative number, it's going to be positive anyways because negative and negative cancel each other out. But when I divide this, or when I divide this by this, I'm going to have a small number. So I kind of like working with big numbers. It doesn't really matter which variable you want to solve for first, but I'm going to solve for x, okay? So in order to do so, I'm going to divide this x value to this side. And we see when I do that, we're going to have a value of x equals to 3y. So it's a big feat. I have my x. So what do I do now? I'm going to plug it into our capital F lambda equation, okay? That's going to equal, and that's found in step 3, if you guys forgot. I don't want to throw you off. We're going to plug it into this equation here that we found in stage 3, just like we've been doing for the rest of the problems, all right? And that equation was 60x plus 120y minus 600,000 equals to 0. So when I solve for x, let me put this on the charger. We're going to have 60 times 3y plus 120y equals to $600,000. All right, boom. All right, we're gonna go ahead and crunch these numbers in. When you put in the calculator, let me pull this up, make sure. 60 times 3 equals to 180 plus 120. That's gonna give us 300y. And that's gonna equal to 600,000. Now I want y by itself. $600,000 divided by 300 equals 2,000. Woo! 2,000 is y. All right, now we have y. We can solve for x. X equals 3 times y, which is 2,000, which equals to 6,000. Alrighty. So essentially, we found out that the production of let me go back to the equation. Whereas the production, what should determine the amount that should be allocated to maximize production and maximize the and find the maximum production. Okay, so the production will be maximized when using blank units of labor. So we established that X was our unit of labor. So we have X here, 6,000 units of labor, and Y was our units of capital. So we have 2,000 units of capital. All right. And in terms of finding the maximum production, which is this here, we're going to plug our x, y values into this equation here. And I'm sure you guys can do this with the calculator. And just make sure you round to the nearest integer. And when you plug that in, you're going to get 231,982 units. All right. And that wraps up this video tutorial. Thank you guys for watching. I know it seems a little tedious. Go back and kind of read through what I'm doing. I'm telling you, this is not something that you want to complicate inside your mind. It's very simple math, and I'm sure we all could do it. We made it this far, so let's just keep going. Thank you guys for your time.